Hello, welcome back. Now we're looking at 3D systems of a Brillouin zone and reciprocal lattices. Well, I gave you in the previous section a prescription on how to solve for the reciprocal lattice vectors in a two-dimensional system, and now I'm just going to give you the recipe for a three-dimensional system, and then we'll explore a little bit more. So here was the complete recipe for 2 dimensions. Here, 2D. And we're going to do this now for 3 dimensions. All we're doing is, right now, is giving it a third vector for the third space, and we expect to see a third vector in the reciprocal space. And again, A1, A2, A3 are vectors, so are B1, B2, B3. And the n's and the m's are any integer. And really, Rn is to be representative of a primitive Bravais lattice vector, and we know there's 14 of those. And here's the recipe as you go from real space into reciprocal space. So I'm not going to derive these expressions. You can find derivations. It's probably interesting to read here this Wikipedia article or to look at your textbook. But what you see is that B1 is orthogonal, a rotation out of A2 and A3. B2 is orthogonal, or a rotation out of A3 and A1. And here you have a cyclical permutation that B3 is then also a rotation out of A1 and A2, and orthogonal to these vectors. All right, and then you see in each term you have a normalization of that numerator against a dot product of the original direction that you're coming from. So B1 is normalized by A1 times a rotation of 2 and 3. Okay, so all of this is then a cyclical rotation. And just as a quick check, you can see that Gm times Rn must be 2 pi n, given these cross products. This is the full 3D recipe. That's it. So I'm just going to appeal to some symmetries, right? I mentioned here rotations. Remember, there was a rotation here in 2D space. Now, a cross product is the rotation in the 3-dimensional space. The same kind of normalization you have, it's just the details are slightly different. All right, I mentioned this is the full recipe. We know that there's really only 14 3-dimensional Bravais lattices. So there's really, again, a limited number of things as a mechanical piece one could test. The understanding of how to make orthogonal Bravais vectors, right? So it's really a limited set. And just as a reminder, you can use the Wigner-Seitz algorithm for unit cell reciprocal space calculation or identification. Here's the graphical memory again. So in order to get a unit cell, a primitive unit cell, you connect each of the neighboring lines like this. You divide each of these lines by half, like this, and like this, and like this, and this like this. And you should get something that looks like it, okay? So now let's take an example of a 3D cube. So we're going to calculate the Brillouin zone, the Brillouin zone and the reciprocal lattice of a cube. Just to appeal to some intuition, I mentioned that the new vector B1 in the reciprocal space needs to be the rotation out of A2 and A3. And that means A2 and A3 are orthogonal to each other in a cubic lattice, that we know that that is parallel to A1. Now, similar to this here, B2 is the rotation out of A3 and A1, and we know it needs to be orthogonal because that's part of the cross product. So this is parallel to A2, so we know B2 is parallel to A2. And basically, you can rather rapidly see that a perfect cube has the reciprocal lattice of a perfect cube. And of course, then the Brillouin zone is also identical. All right. And again, use the Wigner-Seitz algorithm if you have doubts on determining the primitive cell. All right. Now let's get to more complicated things, like a more realistic crystal like silicon or gallium arsenide. In the previous lectures, we had identified that these lattices are two FCCs that are interlaced with each other, and with a basis vector of 1/4, 1/4, 1/4. And you can derive that the reciprocal lattice of a diamond lattice is BCC, or body-centered cubic. All right, so those two lattices are Fourier transforms of each other. And if you want to obtain the Brillouin zone of this reciprocal lattices, what you find is that it gets a surface that looks a little bit more complicated. Okay, so let's explore this Brillouin zone a little bit more. There are some definitions in it that as you march along from the central point, that's typically called a gamma point in a lattice. As you march along the x direction, or kx, ky, kz are symmetric. You have a Brillouin zone edge. You have a surface here that's called the x point. The line from gamma to x is called the delta line. If you're going into the diagonal, into 1, 1, 1, 1, so you're going down here into this diagonal, you actually find that the lattice constant 2 pi over a, which is here in the cube, is not the ending point of the Brillouin zone. It's actually at 0.87 2 pi over a. Okay? So the edge of the Brillouin zone into the 1, 1, 1 crystal direction is not exactly 2 pi over a. So it should be pi over a. I'm sorry, that's what so this should be pi over a here. Okay? Pi over a. Okay. Now, the important thing to note is that the Brillouin zone is space-filling, just like the real space is space-filling, right? The space is completely filled with a repeated unit cell. So if you have a Brillouin zone that is a reciprocal space, it will be space-filling. They stack slightly different than the perfect cubes that you might usually imagine, but they stack with each other. And we have the critical conceptual step here is really that we have transformed a real space representation like Rn, that is a periodic physical property. We want to represent that into a reciprocal space, which is the Fourier transform, and we relate the Rn and the Gm as reciprocal to each other. We need to choose a basis set wisely. So for repeated cells, periodic cells, the plane waves work really well. And that's why we use a Fourier transform to relate these orthogonal vectors with each other, these orthogonal spaces. In 2 and 3D, the reciprocal space have critical axes and symmetries. And we will look at properties along those critical axes and symmetries. Now, given a basis, we can then calculate things like Schrödinger equation and band structure and extract coefficients of strength of these Fourier expansions. And we calculate wave functions on top of that basis. So, and again, we'll look at solutions of the Schrödinger equation along critical paths along the Brillouin zone, and we'll also learn how to look at surfaces of energy, etc. And that's what we'll do in the next sections. Okay, so here's the summary. I gave you the recipe for a 2D reciprocal space transformation. And here's the recipe for a 3D reciprocal space transformation. With these recipes, you can transform any of the 5 or 14 Bravais lattices in 2 and 3D respectively into their reciprocal spaces. So that ends section 8 on Brillouin zone and reciprocal lattices. Thank you.